A diagnostic radiograph is only as reliable as the physics capturing it. When those physical constraints are unmanaged, a perfectly sharp anatomical map collapses into a blur of useless noise. Radiographic quality is a zero-sum mathematical optimization problem rather than a simple collection of machine settings. Three core physical variables dictate the final image: spatial resolution, contrast, and quantum noise. They constantly fight for dominance. Pulling on one variable mathematically forces a compromise in the other two. To understand how an image is formed, we have to deconstruct the equations that establish the physical limits of these three variables. We will then map these physical boundaries directly to the clinical quality assurance standards designed to police them. Understanding the math allows a clinician to identify a hardware failure before the system crosses the threshold of diagnostic validity. We begin with subject contrast. This is the physical ratio of radiation intensities exiting different tissues. Contrast depends on tissue attenuation differences. 1,000 photons strike two tissues. Block A absorbs 50%, leaving 500. Block B absorbs 90%, leaving 100. Display densities vary logarithmically. These emerging photons become logarithmic values of 2.7 and 2.0, generating a contrast difference of 0.7. We can maximize this attenuation ratio by reducing the tube potential, known as the kV, or by introducing materials with vastly different atomic numbers, like a barium contrast medium. That physical phenomenon is completely separate from image contrast, which is a post-processing digital manipulation of the captured data. This gradient scale represents Hounsfield units from -1,000 to +3,000. By narrowing the digital windowing width around a specific center point, we force all values outside those brackets to display as solid black or solid white, highlighting target tissues. Software can stretch the visual display to help the eye, but it cannot manufacture diagnostic contrast if the original data is destroyed by scatter. Next is spatial resolution, the minimum physical distance required to distinguish two separate details. We measure a system's ability to capture fine detail using the modulation transfer function, or MTF. An MTF of 1 means perfect line reproduction. As lines move closer, spatial frequency increases. The system struggles to resolve narrowing gaps, and the MTF drops toward 0 until the lines blend entirely into a homogeneous gray. The first hardware limitation causing this blur is the physical width of the detector aperture itself. If an anatomical detail is smaller than a single detector element, its signal is mathematically averaged with the surrounding tissue and erased from the image. This introduces the ultimate mathematical boundary for digital imaging spatial resolution, the Nyquist criterion. The Nyquist theorem states detector sampling pitch must be at least twice the highest signal frequency. Here, a 2 Hz sampling grid attempting to capture a 4 Hz wave entirely misses the peaks and valleys, drawing an incorrect flat line. No matter how high you push the radiation dose, anatomical data that exceeds the system's Nyquist limit is permanently invisible. When we manipulate that dose, we encounter quantum noise. This is the random statistical variation of photons hitting the detector that obscures the anatomical signal. While the total amount of noise increases as more photons reach the detector, the relative proportion of noise in the signal actually decreases. It drops as the square root of the photon count. To reduce this noise proportion without increasing patient dose, we can use larger detector elements, providing more surface area to absorb photons per pixel. However, increasing detector size forces a mathematical decrease in spatial resolution, enforcing the zero-sum reality between our three core variables. The final major degrading factor occurs outside the detector entirely: geometric unsharpness, caused by the physical geometry of the X-ray tube. Because the X-ray focal spot is not infinitely small, radiation projects from multiple angles. This width, multiplied by the ratio of the object and detector distances, creates a blurred outer edge called a penumbra. Image blur and noise are never random errors. They are calculable physical constants dictated strictly by tube geometry and photon statistics. Because hardware inevitably wears down over time, these physical constants will drift if left unmonitored. Hospitals rely on strict quality assurance protocols, specifically IPEM Report 91, to measure and bound this physical drift. These protocols establish two testing thresholds: a remedial level, requiring immediate calibration, and a suspension level, where the equipment is legally unfit for diagnostic use. We can track geometric unsharpness directly through the annual focal spot measurement QA test. By imaging a star test object, physicists intentionally create a spatial frequency failure. By measuring the exact diameter of the central blurred zone, they calculate the precise physical degradation of the focal spot. The MTF and spatial resolution limits are similarly tracked through QA tests conducted every 4 to 6 months. A lead grading resolution bar pattern is imaged to ensure the system hasn't suffered a 25% drop from its baseline resolution. A hospital's QA manual is a scheduled series of physics experiments designed exclusively to detect subclinical hardware decay. Every diagnostic image is the result of competing physical trade-offs. Pushing the system to maximize spatial resolution starves the detector elements of photons, instantly increasing noise. Optimizing subject contrast demands strict control over tube energy and scatter radiation to maximize tissue attenuation differences. This table details the clinical quality assurance standards. They serve as the mathematical tethers that hold these physics in place. These precise thresholds guarantee the physical realities of the tube and the digital detector never drift beyond the limits of diagnostic certainty. Knowing how to interpret a radiographic image requires knowing the exact physical limits of the machine that generated it. When a system is returned to perfect calibration, the physical variables balance, and the anatomy snaps into pristine focus. Mastering the radiographic system's physical boundaries is as essential to diagnostic power as recognizing the anatomy itself.